Good afternoon, class. So you guys know that, let's see, this is week 9 of the semester, so advisement starts this week. Some of you are my advisees, and you should have gotten an email this morning about signing up for an advisement appointment. And like the spring, we're going to do advisement via Zoom. So make sure you sign up. If you're my advisee, I prefer at least a day in advance so that I can have time to send you the Zoom link for the Zoom conference. If you're not my advisee, look for an email from your advisor. If you don't know who your advisor is, you should be able to see who it is on Rail, and if you don't know how to check on Rail, just ask me. I'll try to figure it out for you. All right. So yeah, advisement this week for spring, and spring schedule is already posted, so you can go there and look and see what classes are offered. I'm guessing some of you will be in Capstone in the spring. I'm teaching Capstone. I'm teaching physical computing in the spring, and but the schedule's posted, so you can start building your schedule for the spring. And all right, enough of that. So hope you had a good weekend. It was a beautiful fall weekend. And today we are going to take a look at take one more look at the project that we were working with last week, and we'll talk a little bit about Practical 2, and then we'll get started on some new material, which is in Chapter 9 of the book. And if you're keeping track, Chapter 9 is the second to last chapter. There's one more chapter after that, Chapter 10. And so we're almost through the material in the book, and we're almost through the material in the workbook for the lab. And we're coming up to a point where we're going to shift focus, and you're going to do more independent work on your projects. Okay, so that's coming up not too long. Week 9 already. We only have 4 more weeks. It's crazy. It's crazy how fast this semester's going. Hi, Justin and Logan and Alexis and Cole and Brianna. All right, so here's the main reason I want to revisit the project we were working on last time is I figured out, I don't know if you picked up on this, but I was frustrated last time when we were looking at these visualizations of the space-time cube, and you could zoom in and pan. So you got zoom, 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 zoom. Pan is you click and drag, so you can pan left, right, up, down. But what I was really wanting to do was orbit, and I couldn't figure out how to do it on Friday. Well, I changed mouses, and now I have a mouse that has a center mouse button that I can click, and drag. Ooh, 3D. 3D map. So this was the last iteration of this visualization of the space-time cube, where we're looking at these hotspot visualization of the hotspots. So red spots are statistically significant hotspots, where there's more crime than the gray blocks, and the blue spots are statistically significant blue spots. So yeah, you just got to click. You need 3 mouse buttons to achieve this. And then you can click and drag, and this is called orbiting. There's the Atlantic Ocean. All right, so we'll get a chance to do some more of this today with some different data. All right, you guys got any questions while we're working? Make sure you post them up in the comments in the chat window, and I'll take a look. All right, so I wanted to show you. Let's go over to Chrome. There we go. So on the Sakai site, under assignments, you'll notice that now Lab Practical 2 is an assignment, and it's open, although don't complete it yet. It's going to be a performance assessment that you do on November 5th, lab on November 5th. So that's a little over 2 weeks from now. And but I finalized this assignment. So if you go to this assignment, you can read about it, and you can start practicing. And you definitely need to practice. So the parameters have changed a little bit from the way I had talked about it originally. And the parameters are that I'm no longer going to give you a project package. I'm giving you a geodatabase. Okay, so what I've supplied you with is a zip geodatabase, and if you go to Resources, Lab Practicals, Lab Practical 2, here it is. It's zipped up. It's a geodatabase. So you can download it. It's like 40 megabytes. And when you unzip it, you can add that geodatabase to your project, to a new project. Start a new project in ArcGIS Pro. You can add that geodatabase and you can start exploring the data. And instead of giving you 3 feature layers, feature classes, I've given you 4 feature classes. So one is the boundaries of all lands administered by the National Park Service, NPS boundaries. One are polygons, so this is polygon feature class. Another polygon feature class, U.S. county boundaries. It's the boundaries of all the counties in the United States. And each county, in the attribute table, each county has some demographic information, including population. All right, U.S. major cities is a point feature class. And it shows the locations using points of major cities in the United States. I'm not sure what the criteria is for a major city, but one of the dimensions in the feature class is the population of the cities. Okay, and that will be important. And then I've given you one more feature class that only has a single feature in it. And so what this is, I made this from the U.S. states, deleted Alaska and Hawaii, and then dissolved all the other states into one big giant polygon. So I called it U.S. contiguous states. It's the the lower 48. It's sometimes referred to, although I don't know why they call it lower, because I guess on a map, if north is up, then all the states are south of Alaska, except for Hawaii. Anyway, the U.S. contiguous states is the 48 states, not including Alaska and Hawaii. Okay. So these feature classes are are also available. Let's go to ArcGIS here. So they're already on this. I put them on this map here that you're seeing right here. But if you search for data in ArcGIS in your organization, you should be able to find, I think I put this in a folder. I wonder if we'll be able to find this folder. It's called, let's search for practical. Well, we'll just search for the names of these feature classes. Hold on, I realize this is too big. You can't really see it very well, can you? Let's try that again. So you should be able to find these on, if you search ArcGIS Pro, add data through the portal, My Organization, Should be able to find these layers. Let's see. Yeah, okay. So you know it's the right layer if I'm the owner. jgroff7 is my username on ArcGIS Pro or ArcGIS Online. So U.S. major cities is a shared hosted feature layer on ArcGIS Online, and then these other layers are there as well. So let's see, MPS boundaries. There it is, MPS boundaries. So these feature layers, they're all hosted. So you can add them to your map that way, and then you can put them. If you do it that way, you know, if you download the geodatabase that's on Sakai, and you know, over here you can go to database, add database, and then you can navigate to where the database resides on your local computer once you download it and unzip it. If you don't do that, if you use the add data and you pull this data from ArcGIS Online, make sure you export those layers to a new feature class in a local geodatabase before you start to operate on them. All right, and do apply tools to them and do analysis on them. All right. All right, back to Chrome. Let's see. All right, so your mission in this practical exam will be to use this data in ArcGIS Pro to answer 2 specific questions. So these questions haven't changed from the last time we talked about these. Which national park in the 48 contiguous United States, so that's the 48 states not counting Alaska and Hawaii, is furthest from a U.S. city with a population of 20,000 or more? So you got to start thinking about, well, how are you going to answer that question? What tools are you going to use? What kind of queries or what kind of selections are you going to apply to your data to make sure you're answering the question correctly? And the second question is, how many people live within 50 miles of the Appalachian Trail? So you're going to show off your analysis tools, your skills using analysis tools in ArcGIS Pro. This is the majority of what we learned since your first practical exam. And so you'll start by creating a new project and adding the geodatabase, unzip it first. Or you can add the hosted feature layers that are on ArcGIS Online to your project. And then I'm going to want you to create 2 separate maps. One map to use to answer the first question, and one map to use to answer the second question. I want you to make a layout of the map that you use to answer the first question and share that as a PDF. Use a graduated color symbology to show that the distance from each national park to the closest U.S. city with a population of 20,000 or more. And then I'll also want you to create a project package and share that with me. Okay, so the graded work in this case is going to be a PDF of your layout, and you can attach that to this assignment. And our answers to the 2 questions above in a text box. Hold on. Let's go to student view so you can see. There we go. Okay, so there's a place for you to attach your PDF and attach a project package. So this last one, I'm not sure this is going to work because your project package is going to be a really big file. So we have to come up with a different way to share your project package. So we may not be able to attach it here. Let me give that some thought. Might have to do something different besides attaching it to this assignment. All right. So that's Practical 2 in a nutshell. And so the week after Practical 2 is your second exam. And then the rest of the semester is going to be spent working on your projects. And I know I haven't framed the parameters of your project yet, besides saying, you know, find some data, spatial georeference data that you might want to work with. So I'll work on that this week and clarify the expectations there pretty soon. All right. Okay. So let's go to. So I put an announcement on here. I didn't notify you of this announcement. Excuse me. But there's the data that is used in Chapter 9 in your textbook deals with this vineyard. It's like over 4,000 acres. It's a vineyard in Monterey County. Is that a county in California? And it's this vineyard uses GIS to inform I don't know, pretty much every dimension of their operation. And so the data in Chapter 9 and the process that we'll go through when we look at this data from Chapter 9, it's called suitability analysis. So the idea is we're going to look at data about the landscape at this vineyard and try to determine where a good spot for a new vineyard to plant a new vineyard will be. So, but this chapter has a link to this article on Esri's website about this vineyard, and I posted up here in an announcement. So you guys should check this out and read it. It's pretty impressive. Yeah, Monterey County. So apparently this is like the best place in the world to grow grapes for really long growing season because of the geography and because of the maritime influence. And they even do, so they use GIS to like answer questions about their their land, where suitable locations will be for new vines. They keep track of where their current operations are, and we'll even do something called it's called geofencing. And geofencing is it's like in a GIS you could draw a polygon around your farm, or you could even draw polygons around the individual fields on your farm. And then your farm equipment, your tractors, your harvester, you can have a GPS unit in there. And if that tractor then is web connected, has some ability to relay what its GPS coordinates are, you can tell when that piece of equipment enters or leaves that field or that farm. So you can keep track in real time of where all your equipment is, where it's being utilized, how many hours it's being utilized in different locations. And so a geofence is this virtual fence, and anytime a GPS tagged resource enters or leaves that virtual border, that virtual fence, that triggers an event, and those events can be kept track of. So I guess that this is something like this has been done for a long time with people on house arrest. They're wearing those anklets, and the police can tell if you leave your house because of there's a perimeter established, and the GPS coordinates exceed that perimeter, there's an alert that's created. All right. So it's an interesting article, and they even do like, here's a map that they're creating to classify various fields as being appropriate for different types of skill level when it comes to harvesting. So like slope, here's these fields have, this field has a lot of slope, and that makes it harder to harvest in that field. You may not be able to use the mechanical harvester in this field because the slope is too severe. Now these fields over here have much less slope, so they're easier to harvest. Okay, anyway, it's a cool article. You should take a look at it. All right, let's go. Let's go here and okay. So let me open this project. It's called Vineyard. Oh, great. ArcGIS isn't responding. Okay. All right. So here we go. So this is a line feature that is outlining the this vineyard. It's called Shade Vineyards. Shade Vineyards. What is it called? Hold on. Yeah, Shade Vineyards. Shade Vineyards. So this this is data that this article is talking about. You can see, look at it. It looks the same. The outline looks the same. So in this lesson, we're using data about this actual vineyard. Okay, so this outline of the farm is of the vineyard property is just a line feature. See that? And so we're going to want to convert this line feature into a polygon. All right, so we'll do that. Not quite yet. Let's look at this other data. So these layers are raster layers, and we haven't used raster data very much. We generated some raster data when we used the kernel density tool, but this is raster data, and this data is referred to as a digital elevation model. Digital elevation model. So let me just turn on this one. We'll zoom in here. I was hoping that it would be a little. Let me go somewhere where the contrast is more so we can see these individual pixels. Okay, so I think you can see that now. So what is raster data? Well, it's data that is a grid. It's a grid of pixel values. So raster data is a lot like an image. It's like a digital image. It is exactly a digital image. There's there's some differences though. One difference is the pixels don't necessarily all have to be uniform size. The pixels can be different sizes, and that's that reflects the fact that this is used to represent geospatial data on a curved surface. So an example of that is a lot of satellite imagery that we use comes from Landsat satellites, and Landsat imagery has a resolution of about 30 meters on the ground. So that would suggest that the pixel size in a Landsat image is 30 meters. but it's not uniformly 30 meters. You know, if you look at Landsat imagery projected onto a 2D surface, some of the pixels get stretched in one dimension versus the other dimension, and you know, that just reflects the fact that it's, you know, it's, you can't project a three-dimensional surface onto a two-dimensional surface without some sort of distortion. And that happens with raster data as well. But here, you know, these pixels are all, they look very uniform. And if you click on a pixel, you'll see its value. So this pixel has a value of 150, 149. This pixel is 144, 142. So darker pixels have a lower value. 120, 116, 112. And you can see, you know, these brighter pixels are higher, 205. So what we got going on here is this, so this raster data that we're looking at here, this digital elevation model, the color, well, is going from white to black. It's grayscale, and the color corresponds to elevation. And we, you know, I actually there's going to be some baseline elevation, and you know, so maybe relative to sea level or something like that. And each of these pixel values corresponds to some value relative to that baseline. I don't know what that is here, but what we do know is that let me zoom out here a little bit. That some of these let me go here and see if you can figure this out instead of me telling you. So if you look at this picture, you know, there's obviously no information out here at the border. If we zoom in here, can you figure out what's higher elevation? Is white higher elevation or is black higher elevation? Can you guys figure it out by looking at this? If you think you know, put it in the comments. So a big clue is these features right here. What do you think these features are? These long, skinny tendrils. Good, Sean. White is higher. White is higher elevation. And the darker color, the blacks and grays, are lower elevation. Right, they're streams. They're streams. They're little creeks. And maybe they're not even like, they could just be like seasonal creeks. It could be just, you know, features in the landscape that were carved by heavy rain. But so that's what we're seeing here. So white is higher elevation. So that corresponds to a pixel value that's higher. So you know, this type of data, it's let's see here. Let's take a look at a histogram. Okay, so I don't. Let me do that again so you can see what I'm doing here. So let me actually, let's turn off NED 2 and look at NED 1. So right click. So this is raster data. We got some special tools here. Right click on it and I can do create chart, and let's look at a histogram. And we're going to look at band 1. There's only one band in this histogram. It's from white to black. And take a look at the distribution of pixel values. So the red line represents the mean. The median is the purple line. And standard deviation are these gold lines. But you know, this is not a normally distributed distribution at all. You got all these lower pixel values, these blacks down here, but this is probably artifacts from the periphery where you're not actually seeing real data. But you look at the data points here, and it ranges from about 105 up to 222. So it's not unusual for you know, here the pixel values are floating point numbers, so they have decimal places, but it's not unusual to find digital elevation models that would be like 8-bit, and 8-bit means it can represent numbers from integer numbers only, no decimal places, from 0 to 255. And so you would map whatever you're representing, in this case elevation, onto that range of values. All right, you guys take physical computing next semester, and you'll learn all about binary and bit systems and 8-bit versus 16-bit and that sort of thing. All right, so you know, there is a ton of information here. You know, each of these grid points has a value associated with it, and that value encodes information about elevation. And there's a ton of information there. And there's actually two bits of two raster layers. Delete that chart. Delete this chart. And when you zoom in here at the border between these two raster layers, these two digital elevation model layers, this second one is needed to give us some information about this northwestern corner of the property. And if I zoom in here, you see this rapid transition from you know, from one image to the other. So it looks like there's a discontinuity. It looks like you know, what it looks like when you look at it like this, what it looks like is that the one image is using a different scale, going from white to black, than the other image, and that's not exactly true. What's actually happening here is the symbology is different. So when these rasters are rendered on the screen, the ArcGIS Pro assigns, you know, one value to white and another value on the other end to black, and then it scales the values in between as shades of gray. And with these two rasters, because they're different sets of data, those endpoints are set differently. So the color scale is different in the two images, but actually the data is, so we zoom in here, let's take a look. So if I click right here, you see, oh, hold on. Alright, so I click right here near the intersection. You can see that NED1, the value of the NED1 pixel at that point is 146.62. The value of the NED2 pixel at that point is exactly the same. So the data does overlap, they're just using different color. Oh, hold on, sorry. Alright, now let's try that again. So if I click right here near the intersection, you see NED1, 146.57, NED2, 146.57. So there is a correspondence between the data in this raster called NED1 and this raster called NED2, and the only reason they look different on ArcGIS Pro is because they're using different color scales. The color scales are different, but the pixel value at a given location where they overlap is exactly the same. So when you have a situation like this where you have, you know, another difference between a raster layer in a GIS and an image that a picture that you would have, a digital image, is that typically digital images are rectangular. You know, they have the same number of pixels horizontally at the bottom as they do the top, and the same number. So they got like, you know, they're arrays. They're rectangular arrays of pixels. And in a GIS, a raster layer, it doesn't have to be that way. The raster can have an irregular shape, and you can actually chop or clip a raster using polygon features. And we're going to do that in this lesson to restrict its spatial extent. Except we're not going to use the clip function. We're going to use a different tool called the mask. We're going to use a mask. We're going to use a polygon to mask out part of the image that we don't want. So you can have your regular shapes. But so in this case, where you have two raster layers on the same map, we call that a mosaic. It's a mosaic. And you know, so this is when you look at imagery in Google Maps, you're not looking at one picture of the entire globe. You're looking at a mosaic, and it's thousands, millions maybe of individual satellite images that have been weaved together, that have been stitched together. And it's actually to the extent that, like, if you're looking at, you're sometimes like really aware of this because you'll zoom into a place on a map, and like the color of stuff here is a little bit different than the color here, and there's like a border between those two regions, or the resolution here is higher than the resolution here. But what Google actually does is to make these mosaics is one of the problems with creating a satellite imagery based map of the United States is if you take a picture on any given day, a large portion of the United States is going to be under cloud cover. Another problem is this imagery is coming from satellites, so those satellites can't go anywhere, they're in orbit. So Landsat, for example, as it goes over the United States, is going to take pictures of a swath of the United States, and then the next time around it'll take a picture of a slightly different path across the United States, and you can stitch them together. So they're not even going to be pictures that were taken at the same time. And if you pass over this region and there's a cloud there one day, that image, maybe you can use some of the pixels but not the others. So Google will actually like layer together all these Landsat images and will take get rid of pixels that are cloud cover and use pixels that aren't cloud cover, so they can actually weave together on the pixel by pixel basis. And another thing that you can do is called the greenest pixel. You can take a picture of the same point on the Earth multiple times and use the greenest pixel from that collection of mosaics to represent that spot. All right, so this is called a mosaic. Weave together, you can weave them together. So in this chapter, what we'll do is create a new raster from this mosaic. So the mosaic is the two separate rasters, and we'll weave them together to create a new raster from this mosaic. All right, so let's do a couple of these things, and then we'll pick this up on Wednesday. Keep going. All right, so the first thing I want to do, let's turn these digital elevation models off. Let's take a look at satellite imagery. So there's our farm, our vineyard. You can see fields. And what we're going to do is we're going to use a tool to convert this property boundary to a polygon, because right now it's just a line, and we want it to be a polygon because we want to use it to clip or to mask out part of these digital elevation models. So let's see, feature from No, not feature to line. We want line to feature. No. Feature to, we want a polygon. Where is this tool? There it is. Creates a feature class containing polygons generated from areas enclosed by input lines or polygon features. So that's what we want, and our input feature is this property boundary. And we'll just call the output property boundary polygon, and we'll preserve attributes, run, and so there it is. So you can see this new polygon that was created, which is symbolized with this beautiful aquamarine color. Maybe I'll make it a little transparent so we can see through it a little bit. Here we go. And it's now a polygon. So we'll get rid of this other layer. Okay. I'll leave it on the map for now, the property boundary. So this property boundary polygon, we can use to clip these digital elevation models to just the regions we want. All right. So let's do that. Let's do NED1 first. All right. So we'll look for a tool here. So there is a clip tool. Clip raster cuts out a portion of a raster data set, mosaic data set, or image service layer. So it's a little bit nebulous to me what the difference is between this raster clip tool and what the raster mask tool does. At one point, I didn't know that the clip tool, you could only use like rectangular, you can only clip to rectangular geometries. I'm not sure if that's true anymore, but let's use the mask tool here, because the mask tool, you can use any polygon of any shape to clip a part of a raster that you want to use. So let's try to find that tool. Mask. And let's see. Here, this one right here. Extract by mask. Extract the cells of a raster that correspond to the areas defined by a polygon. So our input raster, we'll do NED1 first, and we're going to clip it with this polygon that we just created, and we'll call it masked NED1. How about that? Okay, and let me turn this off, and you can see. So you see what happened there? It clipped NED1, this raster layer for NED1, to the geometry defined by our polygon. Cool stuff. So we're going to want to do that again with NED2, and we'll call that masked NED2, and we'll run that, and there it is. Okay, so yeah, I'll just pull all this stuff down here to the bottom. I'll leave that old stuff on, but the layers that we have now that we want are these clipped or masked digital elevation models, NED1 and NED2, masked NED1 and masked NED2. All right. So last thing today, let's merge these two rasters into a new raster. So again, this type of situation that we have, where we have multiple rasters on the same, so we have more than one raster layer on the same map. The map is called a mosaic. And so now we're going to want to use a tool that takes this mosaic and creates a new raster from it. Okay. So let's do that. So we'll search for the keyword mosaic, and here it is, mosaic to new raster. Merges multiple raster datasets into a new raster dataset. So our input rasters are MaskNet2 and MaskNet1. Our output location, we'll put it into this same geodatabase that we're working with here. Vineyard. That's weird, I can't find it. I'm looking for the geodatabase. So when I want to create a raster and I want to put it into geodatabase, but I don't see it here. Am I looking in the right place? Hold on a second. Detour. It's in, you guys can't see that. I'm looking to see where this is. So it's supposed to be in that. The geodatabase is in that file, or in that folder. Vineyard. That's interesting. Well, let me make a new geodatabase. There it is. Jeez, why couldn't I see that? Vineyard GDB. Try one more time. Huh. Well, let me give it a name here. So we'll call this the NED for the whole vineyard shade property. The spatial reference for the new raster, so the raster images, let me see what spatial reference they're using. They're using Geographic Coordinate Systems NAD 1983, so they're using a geographic coordinate system, but there's no projected coordinate system associated with the rasters. But the property boundary, I bet, is different. The spatial reference here is, yeah, so the property boundary is using a projected coordinate system. It's WGS 1984 based, but it's using a universal transverse Mercator zone 10N, which must be good for this part of California. Transverse Mercator projection coordinate system. So let's create a new raster that has the same projected coordinate systems as our boundary. So I should be able to select it here. Yeah, property boundary. And we'll leave the rest of the features the same. All right, so I'm going to run, we'll start next time. I just looked at my watch, we're out of time. So we'll start next time creating this new raster, and then we'll take it from there. All right. So I'll see you guys on Wednesday. Encourage you to start thinking about the practical exam. All right, and practice, 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 and then you'll nail it. All right.